Welcome to the Fatty Acid Forum. I'm your host, Renee Smith with Virtus Nutrition, and I'm excited to be able to share with you today this hot topic webinar by Dr. Jose Santos entitled Effects of Altering the Ratio of Omega-6s to Omega-3s on Lactation Performance and Immune Response. Now, if you were at the ADSA meetings in Indianapolis this summer, this presentation may sound familiar. Dr. Santos, on behalf of his team from the University of Florida, presented these abstract findings during one of those sessions to a standing room only crowd. And thanks to a little technology and Dr. Santos's interest in the Fatty Acid Forum, he's with us today to share his team's exciting findings with all of you. Well, let's jump into this week's session on the effects of altering the omega-6 to omega-3 ratio. And let me share with you just a bit of background on Dr. Jose Santos, our featured speaker. Dr. Santos earned his DVM degree from Sao Paulo State University in Brazil in 1992, his master's in 95, and PhD in 97 degrees from the University of Arizona in Tucson. He completed a clinical residency in dairy production medicine in the School of Veterinary Medicine at the University of California, Davis in 2000, and then joined the faculty in the Department of Population Health and Reproduction of the School of Veterinary Medicine, where he conducted research and clinics from 2000 to 2007 in Tulare, California. In 2008, Jose joined the Department of Animal Sciences at the University of Florida, where he is currently a professor with research and extension responsibilities in dairy cattle nutrition and reproduction. His primary research efforts focus on the interface between nutrition and reproduction and methods to improve postpartum health and fertility of dairy cows. With that, I would like to welcome Dr. Santos, and as a reminder, please feel free to type in any questions you have in that box in the lower right-hand corner of your screen during the webinar, and Dr. Santos will address those questions at the end. Thank you, and now here is Dr. Santos.
Thank you, Renee, for the introduction. I want to welcome you to the Fatty Acid Forum, and today's webinar will focus on a recent experiment completed at the University of Florida looking at the effects of altering the ratio of omega-3 to omega-6 fatty acids in the diets of dairy cows on performance and immune response. So before I get into the experiment in specific, I want to share with you some data from other studies that we completed in the last few years looking at altering the source of fatty acid in the diet of dairy cows, in particular looking at the effects of sources of fat that contain essential fatty acids. In this first experiment here, we fed cows from dry off to 96 days postpartum, one of three diets. A control diet that contained very low concentrations of unsaturated fatty acids. And it was actually designed to be very low in linoleic acid, one of the omega-6 fatty acids. And then we supplement the diet with either 1.7% saturated free fatty acids, so mostly saturated fatty acids, or 2% calcium salts containing essential fatty acids. So both diets, the SFA and the EFA, contained the same amount of total fatty acids, which were higher than the control. And one of the things that we observed was that milk production increased in cows that were fed EFA. At the same time, feed efficiency was improved. So in this initial experiment here, we had some indication that supplementing fat to transition cows, particularly when the diet contained low essential fatty acid and the supplemental fat contained unsaturated fatty acids, that improved lactation performance. So we decided to repeat this experiment, and now we conduct that during only the postpartum period, and we saw similar responses. Cows were fed one of those same three diets, control, SFA, and EFA, and those that were fed EFA had greater production of fat-cracked milk for the first 15 weeks of lactation. So these results told us that it's possible to manipulate lactation performance by altering the supplemental fatty acid in the diet. At the same time, we had completed an experiment a few years ago. Flavio Silvestri, a PhD student with Bill Thatcher, demonstrated that feeding fat sources containing omega-6 fatty acids, in this case safflower oil, which is the orange bars, regulated the acute phase response of dairy cows. In these two figures here, you see the TNF-alpha and the interleukin-1 beta production by neutrophils that were harvested from cows that were fed either palm oil or safflower oil in a calcium salt form. And you can see that those that were fed safflower oil, rich in omega-6, produce more TNF-alpha and more interleukin-1 beta. So the combination of these results demonstrate that it's possible to influence the animal as a whole, but it can also influence cellular mechanisms that may be important for different functions during lactation. So we designed an experiment to look at the effects of altering the ratio of omega-6 to omega-3, and the focus was on lactation performance and acute phase response. We measure other things within the experiment, but I'm not going to be able to share that with you during this webinar. So for this experiment, we used 45 multiparous cows. They were blocked by parity as either second or greater than 2 lactation, and milk yield during a pre-treatment period. The first 2 weeks in lactation, these cows were fed a common diet, and then they were randomly assigned to one of 3 diets. A diet that contained a ratio of 4:1 of omega-6 to omega-3, 5:1, or 6:1. And the way we manipulate those ratios in the diet was by altering the supplemental fat sources used. We use calcium salts that contain primarily fish oil, safflower oil, or palm oil. So the combination of those calcium salts were used to maintain the same total fat content, to have a very close unsaturated fat content in the different diets, but alter the ratio of omega-6 to omega-3 fatty acids. So we evaluate lactation performance, and I'm going to share with you yields of milk and milk components, body weight, body condition score, blood metabolites, and approximately 70-some days postpartum, these cows underwent a intramammary challenge, and I'll share with you the protocol used for that. As you know, one of the challenges of doing experiments with unsaturated fatty acids and actually feeding unsaturated fatty acids is always the risk of milk fat depression. We want to make sure that we could evaluate the animal and cellular responses in those cows without having potential confounders from induction of milk fat depression. So we designed diets that would promote adequate milk production for a lactation cow, but these diets were low in starch. And the way we did this was by replacing corn grain with a combination of citrus and soybean hulls. So we maintain the energy density in the ration and the fermentability, but we restrict the total amount of starch. So here is the nutrient content of the 3 rations. They were very similar as expected. The calculated NEL based on NRC for a 24 kilogram dry matter intake was approximately 1.62 megacalories per kilo, so about 0.75 megacalories per pound. The diet contained 16.5% crude protein. The starch content was moderate to low, but we maintain energy in the diet by limiting the total amount of NDF from forage, but feeding sources high in NDF from non-forage sources. And the total fat content, the total fatty acid content was approximately 3.8%. On day 75 postpartum, cows that had low somatic cell concentration in milk, 39 of the 45 cows, they were used to undergo a intramammary challenge with LPS to induce an inflammatory response in the tissue as well as systemically. and then we collect a series of milk and blood samples and physiological measurements from those cows to evaluate the inflammatory response. So here is the diagram of the intramammary LPS challenge. You can see the cows receive intramammary infusion with 10 micrograms of LPS from E. coli at hour 0, and then for the next 96 hours we collect blood samples to measure acute phase proteins, concentrations of pro-inflammatory cytokines, hormones and metabolites, neutrophil phagocytosis and oxidative burst, and rectal temperature of those cows. This is how data were handled during the experiment, so very standard procedures for continuous and binary data, so nothing in particular here. So during the first 15 weeks postpartum, as the ratio of omega-6 to omega-3 in the diet went from 4 to 6, cows experienced a decline in dry matter intake. In other words, cows that were fed the R4, the 4-to-1 ratio of omega-6 to omega-3, consumed about 1.4, 1.5 kilograms more dry matter. Obviously, the consumption of omega-6 and omega-3 fatty acids were altered as anticipated, and this is the final ratio that we obtained during the experiment. So cows that were fed the R4 consumed the diet that contained in fact a 4-to-1, and cows that consumed the R6 in fact consumed a diet that contained 6-to-1 omega-6 to omega-3. So keep in mind that the cows that were fed the R4 consumed 1.5 kilograms more dry matter. So here is the pattern of dry matter intake throughout the 15 weeks postpartum. You can see that they start very equal during the covariate period, but following that, the cows that were fed R4 had increased dry matter intake throughout this period. Milk production reflects the changes in fatty acids as well as the changes in dry matter intake. Cows that were fed the R4 ratio produce 3 kilograms more milk, so approximately 6 to 7 pounds more milk. And they also produced more fat-corrected milk. So relative to R6, they produce an extra 5 kilograms or 4.5 kilograms more fat-corrected milk. I want to make a case that to a great extent part of this response in fat-corrected milk was due to the fact that cows in R4 consume more dry matter. Because cows that were fed lower omega-6 to omega-3 ratio produce more fat-corrected milk, consequently they were also more feed efficient. So the 3.5% fat-corrected milk relative to dry matter intake increased in a linear fashion as we went from R6 to R4. So you can see that during early lactation, feed efficiency was high for these cows. So the increments in milk production and feed efficiency were not at the expense of energy reserves. This is the daily body weight of cows that was averaged into weekly means for purposes of statistical analysis. And you can see that cows that were fed R4 had very similar body weight compared to cows that were fed the R5 and R6. There is a small difference at 15 weeks, but that is approximately 8 kilograms or 16 pounds only. And the same is true for body condition score. There were minor differences in body condition score, and for most of the study, cows that were fed the different fatty acids had the body conditions that did not differ among the different treatments. Obviously, every time we incorporate unsaturated fatty acids, one of the issues is a potential problem with milk fat depression. Nevertheless, altering the ratios of omega-6 to omega-3 had no impact on milk fat content, had no impact on milk protein content, and had no impact on lactose content. However, because cows that were fed the R4 ratio produced more milk, consequently they had greater yields of milk fat, greater yields of milk protein, and greater yields of total solids. But no differences in energy concentration in milk, but the greater milk yield resulted in greater milk caloric output. So basically, the cows that were fed R4 produced more milk. Consequently, nutrient output in milk was increased, but the concentration of fat, protein, and lactose did not change. We saw minor changes in blood metabolites with the different diets, minor increase in blood NEFA with the R4, probably a reflection of the increased milk production. Some of that came from additional lipolysis, but really no major changes in metabolic hormones such as insulin, IGF-1, and no changes in BHBA or glucose, showing that these cows were in very similar energy status during the 13-week experiment. As anticipated, altering the fatty acid content of the diets influenced the fatty acid composition of both plasma as well as milk. You can see here that as the amount of N6 in the diet increase, as we go from R4 to R6, the concentration of total N6 increased in a linear fashion, and so did the ratio of N6 to N3 in plasma. Similarly, as we increase N6 in the ration, the concentration in milk also increased. But on the other hand, the concentration of N3 decreased, and that influenced the final ratio of N6 to N3. So both plasma and milk reflect the change that we impose in the diet. So during the LPS challenge, here is the body temperature of cows. There was an immediate spike in body temperature. Every single quarter that we infuse developed mastitis. No major differences among the different treatments on body temperature for the first 48 hours, and no major differences in peak body temperature. The only thing that was noticed here was that cows that were fed R5 had higher peak body temperature, as seen by the red bar, and cows that were fed the R6 took a little longer to reach the peak of highest body temperature measure in the 96 hours after the challenge. Concentrations of glucose and insulin were slightly affected, vary by time. Concentrations of glucose and insulin were not affected by treatment. There was a major time effect, the typical stress response. There was a spike in glucose and consequent increase in blood insulin as anticipated. But diets had really no effect on those responses. When we look at somatic cell count, this is the somatic cell concentration in milk. You can see that the infusion was very effective, inducing a massive influx of neutrophils into the mammary gland. And cows that were fed the R4 had slightly lower concentrations of somatic cell count in the infused quarters. Here is the concentration of the non-infused quarters for all treatments. They did not differ, and you can see they were lower. Nevertheless, they were still high, indicating that the acute inflammation that we induced was also affecting the contralateral quarters, probably because of the systemic response that you will see in the following slides. But the important message here is that there was some indication that by reducing the omega-6, increasing the omega-3, there was some attenuation of somatic cell count in milk. If you look at the neutrophil phagocytosis and oxidative burst, very minor effect, just a time effect, but no dietary effect. On average, 32 to 33% of the neutrophils were able to phagocytize bacteria and kill them in vitro. This is the acute phase response based on production of acute proteins, acid-soluble protein and aptoglobin. And one of the interesting things is that in a series of subsequent slides, as you will notice, was that cows that were fed the R4 ratio, they tend to have slightly less acute phase and inflammatory response. So as you can see here, aptoglobin was less for the R4 compared to the R6. The concentrations of interleukin-6 in plasma were lower for cows that were fed the R4 ratio, as well as the concentrations of interferon gamma. So indicating that the acute phase response and inflammatory response is slightly suppressed when we feed more omega-3 relative to omega-6 fatty acids, and vice versa. So feeding more omega-6 relative to omega-3 upregulates the acute phase response. So to summarize, altering the fatty acid profile of the diet fed to dairy cows by manipulating the N6 to N3 fatty acids that were supplemented improved lactation performance. Obviously, not all that milk came from just adding those fatty acids. Energetically, we could not account for approximately 2.5 pounds of energy-corrected milk. So we think that some of that response was due to altering the fatty acid profile. Obviously not all, because cows that were fed the R4, they consume approximately 1.4 to 1.5 kilograms more dry matter. Efficiency of feed conversion into 3.5% fat-correct milk increased approximately 5.6%, and this is a pretty interesting component. So this is probably indicating that we are altering to some extent cellular function or perhaps partition of nutrients that obviously we don't know the exact mechanism at this point. Reducing the ratio of N6 to N3 in the diet partially attenuated the acute inflammatory response to an LPS challenge. A lot of this was due to the fact that R4 cows had the lowest somatic cell count, the lowest aptoglobin, and the lowest concentration of cytokines in plasma. So with that, I thank you for your attention, and I will be glad to take questions in the next few minutes. Thank you very much.